my name is Terrell France. I'm a professor at Harrisburg University, and I'm a co-organizer for the Philadelphia-Harrisburg Quantum Computing Meetup Group. So before we get started, I'd like to welcome all of you out there. Many of you are from different meetup groups literally around the world. So a shout out to all of you. That's all I've got to say. Let's get to Max. Max, it's all yours.
Hey, great. Thanks for the introduction. Briefly, I am Max Henderson. I'll probably just be keeping my video on here for the beginning. Yes, I'm a physicist by trade. I live here in Philadelphia, so I'm quite happy to finally be giving a talk to a Philly/Pennsylvania-based meetup group on quantum. Done these in New York and several times in DC now, so it's exciting to be able to talk to y'all today. I can jump into it. Apologies, by the way, you might hear some jumping as I have a very cute dog, but she doesn't understand how meetups work. So bear with me if there's some barking, but hopefully we'll be okay. Might just want some, make sure that, Terrell, that everyone can see this.
It looks good from here.
Okay, great.
Oh, let me add quickly. If you check the presentation notes in the meetup groups, there is a link to an area that does contain a copy of Max's slides. Also, it'll be the place where we'll have the recording, the link to the recording stored later. Sorry, Max.
No, you're fine. Awesome. So I think we can jump right into it. I'll try to pause at different sections of the talk just in case that there are any particular questions. As I mentioned, Max Henderson. I work at a company called Rigetti. That is a full stack quantum computing company. We're building quantum hardware from the ground up, and we also have folks like myself who are a bit more at the top of the stack, and we are trying to figure out interesting use cases for these quantum hardware systems that would be relevant to commercial and governmental applications. And one of the areas I've spent the last few years really focusing on is how we can leverage quantum computing for machine learning. I've worked both as a classical data scientist as well as, having the better part of the decade now working with various types of quantum computing technologies. So quantum machine learning is kind of a natural fit for me in a really exciting general area of research. So this talk's going to go through a bit of, this is going to put a bit of a, 101 on how we see machine learning and quantum, and hopefully is interesting. And again, I'll stop throughout the talk at random points and see if Terrell has any chat questions we want to jump into. But without further ado, so just a quick breakdown of this talk. First, talk briefly about machine learning at a high level, and then talk about kind of how quantum fits into that. And sort of this QML or quantum machine learning taxonomy that we can use as kind of a reference point. Also briefly go over some really important, historically important quantum machine learning algorithms, and then dive a bit more into currently what people are looking at in terms of research areas, and finally wrap up, not surprisingly, with current challenges and research opportunities related to those challenges that people are actively pursuing. So just as a frame of reference, I suppose, I believe not everyone in this call probably is a data scientist or machine learning expert. So sort of the lens one helpful lens to think about what machine learning is or does. So, we have a lot of things in the real world we'd like to make predictions of. And some of those things are built using only first principles. So for instance, you might want to make predictions about how charges would move in a field, and we have some beautiful equations that could form a model that makes it very easy to sort of calculate direct predictions based on input data for various electromagnetic calculations. So this would be a model that we build from first principles, and it's, we use these all the time. They're quite useful. Something that is a hurdle, obviously, is you have lots of problems in the world where you don't actually have an exact knowledge of what are the first principles that should necessarily form the basis for making predictions on new input. So these pop up all the time in real world problems. Like, it's very hard to make, for instance, a first principles based model on predicting if pictures are a dog or a cat or a human, something like that. So it's situations and use cases like this where we use machine learning often, and this is where to a varying degree, your machine learning model can still have a pretty strong prior of sorts, which is a little bit more like a first principles model, but it could also be very much driven completely by the data. And essentially, this becomes sort of the way that we make our predictions. We feed in data to this black box, which again can contain all kinds of different tools, neural networks, statistical models, etc. And primarily the predictions are based off of the data, the training data that you feed into this. Both of these again can be used for answering questions and basically, i.e., tell me some fact about training data I haven't seen before, and both of these can predict answers. They both have obvious limitations. Machine learning models are only going to be as good as you have data, and only how much of it you have, and as well as the model itself is going to be bound in certain ways based off of like structural properties. But anyway, so this is kind of like just a high order picture in our head for how we use machine learning, and how it's driven by data and has obviously a lot of tools inside of it. So if we take open the black box, obviously there's quite a lot of different machine learning mathematical operations going inside. So within many machine learning algorithms, we're doing matrix operations. We could be doing some complicated sampling of an interesting energy landscape, applying various kinds of nonlinear functions and calculating gradients, etc. So obviously there's quite a lot of interesting maths in here and subcomponents of quite a lot of machine learning models that could be interesting to augment in some way. So QML sort of involves the study of how we might use quantum computing to provide a benefit over classical computing by looking at how you might be able to use the fundamental technology for improving or replacing some of these fundamental mathematical operations, or setting up a quantum variant of sorts. People are looking for advantages using these quantum systems by looking at a couple main types of problem groups. First off, you might be looking at using quantum machine learning for things that are classically tractable, computationally speaking, but you might still see a performance benefit using quantum. So these would be problems that a classical algorithm ran on a classical computer today could still do efficiently, in a sense, but that you still might get a benefit using a quantum algorithm. And if the size and scope was large enough, that could still be quite important. This second sort of bullet, and we'll talk to this one a lot, there are quite a lot of problems that we just think are very hard classically, that there's not really a tractable way of doing them. So we're forced to make approximations, so to speak. And we'll talk about some of those models more concretely here in a minute. And we think that there's opportunities here for mapping some of these classically intractable calculations to quantum systems and forming, again, a better approximation, or a more efficient approximation, a better scaling approximation using quantum. The final grouping here is also using quantum sort of subcomponents that might replace completely a classical pipeline or augment it in some interesting way. And there's a whole field of using what we call parameterized quantum circuits within various types of quantum neural networks that we'll discuss in detail that probably fall under this bullet that we'll highlight as well. So that's kind of QML at a high level. At a low level, there's just a ton of research. So as much as you guys would like to read, on the archive, or go to, for instance, the Quantum Zoo NIST is constantly maintaining a list of high impact papers, and over time, the count of the quantum machine learning references has gone up. So there's just an absolutely, a pretty rapidly growing amount of QML applications and interesting studies in the literature. So obviously grouping all this together is non-trivial, but again, it might be useful at the beginning of this talk just to provide a bit of a taxonomy for how to kind of ingest and interpret all of this interesting research. And we're borrowing this from the good folks at Xanadu. This was first shown, or I first saw this from Maria Schold, who is an associate there. And this is a nice breakdown to think about where quantum sort of can fall in, how we break it down basically is how the actual algorithm works, and then the type of data that we're running it on top of. So for this talk, we're going to focus quite a lot on classical data that we are using a quantum algorithm on top of, because as I mentioned, there are certain types of problems or certain types of models we think quantum might just offer an intrinsic benefit over the classical approaches. And at the same time, a lot of the most pressing problems that people would love to solve more efficiently today are not sort of quantum data by nature. So these would be classical problems. There could be problems within pharmaceutical industries, finance, you name it, that they have classical data and they want to do something faster, more accurately, more efficiently. And that would be this sort of big box here. So quantum algorithms on classical data, but there's also some relevant, we'll sort of touch on all of these areas a little bit, because it turns out that again, the field of quantum machine learning has some interesting applications and studies within all of these. For instance, within the bottom left-hand corner, this would be classical algorithms on top of quantum data. There's a whole research line in sort of looking at near-term error-prone quantum circuits and trying to actually see if you can do a form of error correction using classical machine learning algorithms sort of built on top as a post-processor of sorts. So using classical machine learning, can we sort of learn better ways by taking in the quantum data that we're measuring to do some error correction and things like that. So anyway, we'll probably touch on all four of these blocks a little bit throughout this talk, but the primary focus one would be on quantum algorithms operating on classical data. And another way that we can break down quantum machine learning in a sort of taxonomy type approach is by thinking about the use cases as well that we'd be using them for. And this is going to also be something that we come to in this talk quite a lot. So there's a lot of sampling use cases. Again, I sort of mentioned before, certain models have complex probability distributions to sample that can be quite hard to do efficiently using classical computers, and some nice properties of quantum systems could help provide better representative sampling. There's also quite a lot of utility currently looking at various types of quantum circuits for classification or functional fitting use cases, generating synthetic data, and the list goes on. But these again are kind of the main sort of reference points that will probably be useful to keep in your head as we step through the rest of the talk. So I think I can stop here really quickly before going to the next section. Were there any big questions so far that were in the chat?
Actually, Max, I don't see any questions so far.
Okay, great.
You got everybody glued to it, though.
Okay, great, awesome. So then we'll jump in quickly, covering a few historically important milestones in quantum machine learning that are important. So a couple algorithms with some really good scaling properties were developed that all leverage Grover's algorithm. So for those in the quantum computing world, Grover's algorithm is probably pretty familiar. It's an Oracle algorithm. This is a great little post here in the document, I think, for sort of explaining the intuition behind the circuit design for Grover's. But it basically is an algorithm that helps you perform an unstructured search. So you have some, long list of, you have some long list and you're looking for a particular entry in that list, and classically that is hard. It turns out that Grover's algorithm can help you do this with a pretty decent quadratic speedup, and so like, or more than that, sorry. So like the square root. Anyway, but yes. So so we look at Grover's algorithm to better search for unstructured lists, and this is just an example of a circuit for trying to find essentially states which satisfy all of these clauses. Ultimately then, Grover's basically every iteration is trying to increase the probability of measuring the particular state in the list that you're looking for. So this is called amplitude amplification, and kind of visually it's shown here, where you are trying to find the particular state, which is shown here in this little red arrow pointing down, and you're trying to sort of flip it, flip the sign, and then do a rotation about the mean of all of your probabilities. So kind of every step what you're trying to do is increase the probability of the, again, state that you're trying to search for, while driving the other probabilities of the states you're not trying to look for as low as they can go. This kind of search pops up in a lot of, as like an integral part for a lot of early quantum machine learning algorithms. So a few of these examples are listed here, and you can Google pretty quickly for finding, the papers on quantum k-medians and quantum k-nearest neighbors. And a lot of the speedups here at the time were very, very good. So using Grover's, you could get a significant speedup over the classical variants of these algorithms, which is, was and is still very exciting to some respect. The problem is that, so for, making this a reality, there's a couple different limitations, but one of the biggest ones is that Grover's requires this idea of quantum random access memory, or QRAM, which currently is quite challenging, and the field as a whole is still trying to figure out how to do QRAM properly. Requires a lot of qubits and also error correction. So basically, long story short, Grover's algorithm is mathematically this pretty elegant algorithm which could have a lot of applicability for quantum machine learning algorithms down the road, but all of these requirements are for sort of next generation quantum hardware. So the kinds of quantum computers we have right now are smaller, error prone, and do not have error correction yet implemented. And that means that really this won't be quite able to be ran in practice yet for some time. Another interesting algorithm that was pretty important for the field is the HHL algorithm, which is named after the three authors on the paper. And basically, they came up with an interesting quantum algorithm for solving systems of linear equations, or matrix inversion, which immediately also led to some pretty interesting algorithms for doing quantum principal component analysis, support and things like supervised clustering much more efficiently than you could do classically. So again, this interesting sort of algorithm for matrix inversion pops up in quite a lot of potentially machine learning applications. And so by using this more efficient quantum methodology, you could get a pretty big speed up over what was classically feasible. But again, there's some problems on the near-term world. So there's a good paper by Scott Aronson called Redefined Print, sort of, again, highlighting the potential drawbacks or challenges for really using HHL in practice. Again, you have a lot of problems with QRAM that can be prohibitive, particularly in the near term. And, the matrix that you're solving for has to have particular properties like sparsity, or else, again, even though there are some potential quantum advantages for like a sparse matrix, these sort of dissolve when those go away. So there's sort of this cautionary tale again for the types of sort of the scope of problems that this HHL algorithm could be useful for. There's also some recent research done by Yuan Tang, who's published quite a lot of things within this field of quantum computing, sort of that we're now called like de-quantized quantum computing. where she did some very interesting research into really trying to do a more thorough evaluation of true quantum speedup compared to the classical comparative algorithms. And it turns out that some of these algorithms, such as the quantum principal component analysis algorithm, if you gave classical algorithms the same assumptions about the ability to efficiently sample and query the classical data in question, it turns out that some of these quantum speedups disappear, and thus there are some interesting, de-quantized algorithms, or we might call them quantum-inspired algorithms, that you could experiment with practice classically, and it wouldn't require a quantum algorithm at all. It turns out she also uncovered a very interesting algorithm which actually showed a speed up even over the previous quantum speed up for a recommendation systems problem, which we have a little bit of, I think, one more slide on here.
Hey, Max?
Yeah.
Quick question. Can you go back to the slide? First of all, a clarification. So de-quantize, that term's being used as really referring to quantum-inspired algorithms? Is that what you're?
Yes, it's sort of like, yeah, sorry, I should differentiate a little bit. So quantum inspired, it's a bit of an umbrella term, but yes, it's typically something that is something you could execute on a classical computer, but that takes inspiration either from a previous quantum algorithm or some quantum mechanical component. But again, is something that you can run purely classically. De-quantized, specifically algorithms that have been de-quantized, it's more when they've been shown that a classical version of the algorithm gets the same speed up as the quantum approach.
Okay.
So her work showed that you could sort of take the quantum out of these algorithms and have a new classical variant, and then that previous quantum speed up was sort of gone. So that refers to the de-quantization process.
Okay. Do you one just popped in, and there's one earlier I'll ask too. So give me two questions here if you got a second.
Mm-hmm.
Are there QML algorithms where there is a strong indication that they cannot be de-quantized?
Yes, that's a good question. So there are some particularly difficult to imagine de-quantization algorithms would be some quantum machine learning algorithms that are also ran on quantum data itself. So these I think would be very difficult to de-quantize because both the model and the data itself is not easily expressible classically, I suppose. So yes, so like one example, I don't believe it's in this slide deck, but there is a interesting algorithm for doing like a quantum variant of a convolutional neural network to predict properties of like an Ising spin glass system. So like, can you predict sort of the phase of this quantum state using this quantum machine learning algorithm? And those I think would have more sound properties. We'll also talk about a model a little bit later in this talk, which I believe IBM published, that is doing predictions again on data generated from a quantum circuit, which again is probably hard to imagine de-quantization. The algorithms that have been really threatened by de-quantizations are ones that rely on some of these like linear algebra, like linear sort of algebra approaches really strongly. I think would be one of the takeaways. Yeah.
Okay. These came in earlier, and actually I think they're pretty good questions because I wouldn't know how to answer it. Can you give examples of what quantum data is and how that data may be different from classical data?
Yeah.
Can you say more about Q data?
Yeah, that's a good question. So yeah, you could think of it like a density matrix, for instance. So if you're trying to describe a quantum system, you might use like a density matrix to do that, and that would be like an example of quantum data, or like measurements from a quantum circuit, so a wave equation, things like that. So yes, that would be, I think, all examples of quantum data.
I think I remember I saw a presentation actually yesterday where I think it was called amplification data. So let's say I had 3 pieces of data, A, B, and C, or 4, D, and each of those were the amplitude coefficients. I don't know enough about it to speak about it off the top of my head, but it's where the data actually became the amplitudes, and I guess that got normalized, et cetera. I don't know. Anyway, I'll get out of your way.
Oh no, yeah, no, it's good questions. Yeah,
we're good on questions here, so all yours.
Okay, great. Yeah, thanks for the great questions. And yes, I can't promise I'll be able to answer all of them as well, but I will do my best. But yeah, great questions so far. Great. So yeah, like this kind of, if we go back to, again, thinking about the taxonomies of quantum machine learning, this sort of approach of, again, this field of quantum inspired applications, this would sort of fall under that CC thing where, again, a quantum inspired algorithm, you can run it on a classical device. So in some sense, it's a classical algorithm, even though it's drawing inspiration from quantum in some respect. But some of these have also been developed for operating on classical data. And there's some really interesting research right now into looking at how these novel algorithms might work in practice. And, is there a benefit in using a quantum inspired algorithm over previous approaches? It turns out that at least in initial investigations seem to show that, there's a lot of nuance here and results of performance can be really data dependent. This is from an interesting paper, again, from our friends at Xanadu, and they were looking at this algorithm I mentioned before where there was a quantum inspired recommendation algorithm. So this is like for recommending products or something like that. And they were, looking at, again, trying to see how this scaled as a matrix. And sort of what they saw was that, like, as the matrix rank increased, I believe, that the sort of the speed up started getting quite bad for the quantum inspired approach compared to classical. So there's still a lot of research here, for, again, seeing, like, are there specific types of problems in the real world where these assumptions actually hold, because kind of the regime that this algorithm holds very strongly, it doesn't look like that's quite as similar matrix as in other natural data sets. So this is still a very promising research angle, but it's still sort of a work in progress to show how this might work in practice. But now we kind of turn again to, next phase. So this is kind of a, past our review of some historically important algorithms in QML, again, namely the Grovers and HHL, which were quite useful for forming a lot of the initial work in the space. There's been quite a lot of interesting research into looking at various types of neural networks and how quantum might be able to impact that. We'll focus on the next few slides on one of these models. In particular, the restricted Boltzmann machine. The machine learning folks are probably a bit familiar with this model. Restricted Boltzmann machines are interesting graphical models. They're energy-based and consist of both visible and hidden nodes. Visible nodes are nodes that correspond directly to features in your data. So you could think about, essentially each of these nodes are a single bit, so it could be 0 or 1, and you have some kind of data distribution that you're trying to train on top of. These would map to all your visible nodes, and then by adding hidden nodes, you sort of add the ability to do some, increase the power of your model to form something that can better fit your data set. And by training all of the weights and biases in this model, you'd like to try to minimize sort of a divergence between some statistical properties, basically by sampling your model, producing data, and hopefully driving that data closer to your data distribution. So more specifically here, the RBM has this particular energy structure where, like we showed before, an RBM is composed of these visible and hidden units, which are the V and the H here in this energy equation. And And then each of these units has both a bias on top of it, which is captured in this B and T term, or B and C term rather, and then also have weights between the visible and the hidden units, which are captured in this weight matrix W, so that if you have a particular visible and hidden bit string and you want to know the energy of it, you'd simply process it using this top line energy function. And if you wanted to know the probability of measuring your particular visible or hidden vectors, then, and I'll just start calling the visible and hidden units together, like basically a state. So if you want to know the probability of measuring this particular state of your Boltzmann machine, it follows a partition function, which is shown here, wherein basically the probability of measuring your particular state depends on the state's energy, but then normalized so that if you added up the probabilities of measuring all possible bit strings or all possible samples in your data set, that all those probabilities add up to 1. One of the interesting sort of first approaches into looking at using quantum for this type of a network is that, classically speaking, these networks were basically intractable to train for a while until specifically the restricted Boltzmann machine architecture was investigated by Hinton and shown to be tractable to train classically using his clever contrastive divergence algorithm. We don't need to dive too much into that here, but in general, training Boltzmann machines can be a bit complicated because it requires an estimation over that, it requires an estimation over this normalization term, which if you think about it, if this is over all possible binary states, this scales exponentially the more nodes that are in your model. So you're sort of never going to have a great estimate of this classically, but luckily there are at least some nice heuristics for sampling from this with a restricted Boltzmann machine. So what we'd like to do using our quantum approach is to use a device which more natively can sample the Boltzmann sort of distribution, and then use those samples generated from a quantum annealer to calculate these first and second order moments of our data set and our model as well. And these drive the updates for this Boltzmann machine. So basically, long story short, the ways in which we update all of our model parameters are typically derived by looking at the first and second order moments of samples from your data set and samples produced from your model. And the goal is that you want to try to train your model so that eventually the samples produced are statistically equivalent to your data set in terms of these first and second order moments, which all that means is basically if I'm looking at a particular node, let's say S1 and S2, the first order moment of S1 is just the probability of that node being measured as a 1. And the second order moment between S1 and S2 would be the probability of measuring both of those nodes as a 1 at the same time. So we investigated using quantum annealers to do just this. This was some research I published back in 2015 while at Lockheed Martin, where we looked at mapping the Boltzmann machine energy directly onto a quantum annealer, which has quite a similar structure, and then using the samples produced from the quantum annealer to train our Boltzmann machine. Because the devices that we had access to at the time were only able to embed graphs with the connectivity we needed that were rather small, we trained on the MNIST data set, which is shown here on the bottom left. This is a data set of handwritten images. And what we kind of were forced to do is take the higher resolution 28 by 28 images and sort of threshold them and turn them into 6 by 6 images. So you see the sort of thresholding that we had to do here on the right. And then we trained on this thresholded data set using both a purely classically trained deep belief network, which uses Gibbs sampling to try to, again, approximate sort of samples drawn from this Boltzmann distribution and then making weight updates in the model. And then we also trained it using a quantum annealing approach. So drawing samples using this quantum device, which more natively samples from a Boltzmann-like distribution. And what we saw experimentally was that, and in both of these plots, we're showing the same kind of thing. On the x-axis, it's the number of training iterations. And on the y-axis, it's accuracy of our model. So 1 is 100%, 0 is 0% accurate. And on the left side, we showed results using a deep belief network, which is just a whole bunch of restricted Boltzmann machines sort of stitched together. And the accuracy over time on the training and test set for this MNIST problem. And as you might expect, training on this data over time on a bunch of different models, your accuracy increases over time on the training and test set as you're training these models. But even by the end of 50 pre-training iterations, the results of the classical approach is still only around 60% or so. Whereas using our quantum annealing approach, it seemed to converge rather quickly. So by about 15 or 20 iterations, all of the models we looked at had more or less converged onto the best possible accuracy we could get on this very sort of coarse-grained data set at this point, because again, we were applying this rather harsh thresholding to all the pixels in our images. So, long story short, again, it seemed like using the sampling properties of these devices, which more natively fit the energy structure of this probabilistic model, provided better training for this particular image classification task. People have similarly done some interesting research using these kinds of quantum Boltzmann machines for reinforcement learning. So this is a pretty interesting paper where they're essentially sort of trying to do like a maze solving problem where there's different rewards and penalties in a 2D grid, and you're trying to train an agent to learn what are the best actions given your current state to take. So this is the typical way that reinforcement learning problems are set up, where you have an actor in an environment, and the actor has the ability to select between different actions with the goal of maximizing some expected reward over time. So, basically train your actor so that given an input state, it'll choose options that statistically speaking would guarantee the best possible reward in the future. And these models, there's been quite a decent amount of research looking into using these types of Boltzmann machine models classically for generalizing over input states to try to, again, learn better action selections for some expected reward, for some number of expected reward steps in the future. And so people also have investigated, particularly in this research, the use of training those types of models using quantum sampling, and the results showed that there was an ability to learn high fidelity choices over a number of training iterations using this quantum sampling approach. This was using simulated quantum annealing, but the results were still promising that this kind of a method could be useful for training reinforcement learning algorithms that rely on a Boltzmann machine type model as well. Probably the strangest use case I could think of to also try to, use quantum sampling for some kind of interesting purpose was in also using a version of a quantum Boltzmann machine for modeling elections. So it's probably not probably not surprising to a lot of people here based in the States that in 2016 we had a national election with some surprising results. And it turns out that one of the reasons people think there was quite a lot of models that predicted that Hillary Clinton would win in the 2016 election, and as she didn't, there was quite a lot of post-analysis trying to understand why that might have been the case. And it turns out that one of the biggest issues with people modeling the United States election is that they were ignoring correlations between states. So essentially, you might be modeling the probability that Clinton would win in New York State and modeling it in a way that's completely independent to like an adjacent state like New Jersey, which is a weakness in your model because, these elections have correlated results. Obviously, there's, the types of populations that are in different states have similarities that should make them more likely to have kind of a correlated event in the event of an unlikely sort of outcome. And so one of the fun approaches we did is we created actually a fully connected Boltzmann machine. So this actually is a much more complicated to train model than the restricted Boltzmann machines that we showed before because they have connections between all nodes in the model. There's not a really efficient way to train those classically at all, but it turns out that there is, that in our experimental results, training them with this quantum annealing approach, we were able to train these fully connected networks where each node in the network represented a state in the United States. And if we measured the node as a 1, we interpreted that as measuring as Democrat and as a 0 Republican. Nothing cheeky there. It was just you had to assign one to the other, obviously. But basically, we were able to train sort of quantum election models where they incorporated correlations between all of the states as, again, the fundamental sort of energy of these quantum annealers are correlated systems. So we really were trying to map this election use case, which is trying to draw fair samples of a correlated system onto the quantum computer. And you see here at the top line, this is in pink, real values generated over time by a very good pollster 538, which actually did give Clinton a only like 70 to 80% chance of winning throughout most of the election cycle leading up to the election. And we show here below it different quantum trained forecasting results where we have different colored lines because they basically had different national election errors that we were coding into it. But as you can see, it has similar structure to the 538 professional modelers, which means that our quantum models were able to learn something structural that seemed relevant based off of polling training data, but also that the quantum models seem to have a lot more, I suppose, error sort of caked into their predictions. Not error as in they're wrong, but more just that the results ended up being much closer to sort of like a 50-50 toss-up, which doesn't at all mean this quantum approach is immediately better than any classical approaches, but more that this is an interesting use case. Sampling fully connected systems for something like an election forecast might be something interesting to investigate in future elections using this kind of quantum approach. The next sort of big topic we can jump into. Sorry, yeah, go ahead.
Next, a couple questions here. First of all,
Yeah.
I see some chatter going on the YouTube channel, and it looks like there's a lot of good discussion going on there. So thanks to the folks who are answering questions there too. There's a lot of good discussion. That's what these meetups are all about. But there's one question. Did you compare against potentially better classical approaches for training the MNIST other than the Boltzmann machines?
So yes, in future work we have done that, and we'll actually get into that in a bit later here in this talk. But no, for this algorithm, since we were specifically looking at these restricted, these deep belief networks, which were built with a bunch of restricted Boltzmann machines, we focused on that basically. Yes, but there's far better, like particularly like CNNs or convolutional neural networks are very state of the art for these use cases, and we do have some further research we'll talk about in this talk, doing a quantum variant of that, but we didn't for that particular piece of research.
Okay, there's another question, but I think we'll save that to the end just because it's the prior topic. So I think that's it. Go ahead. Thanks.
Sure. Yep, sounds great. So realizing I'm talking slowly, or possibly just going through my slides slowly, so I'll try to make sure I'm not falling too much behind on pacing either. So anyway, the next general topic area was for this talk was, so outside of sampling applications, or I suppose as an extension of that, we can also think about interesting use cases for generating synthetic data. So there was a great paper in 2019 from for a use case for basically generating synthetic financial data. And they showed that you could use a restricted Boltzmann machine, which the results of the synthetic samples generated from the restricted Boltzmann machine are shown here on the right in the orange line. And basically, without having to explain everything, the synthetic samples generated from training a restricted Boltzmann machine on this financial data was a better fit than some more typical parametric models used often in finance. So the authors of this paper sort of validated the approach of using a restricted Boltzmann machine for generating synthetic data that seemed to match their financial data quite well, particularly compared to some, I suppose, more standard parametric methods, and opened up the possibility that this could be an interesting opportunity to also investigate using like quantum for helping train and generate these synthetic samples. So we actually did just that, and we did it using an interesting annealing device that we developed, which is actually completely simulated. So this is another interesting application, I suppose, of a quantum-inspired use case. We had done a lot of work in the past with experimenting with D-wave quantum annealers, which are real hardware devices. But we also actually built our own simulated quantum annealer that runs on a bunch of GPUs using a path integral Monte Carlo approach. And the advantage of this simulated quantum annealer is that it's able to capture enough of the interesting properties of some of the quantum approaches on hardware that it seems to be quite good at sampling some of these distributions better than one could do using like a Gibbs sampling type of approach. So this allowed us to do quite a lot of interesting work, both in optimization problems as well as sampling for these machine learning models. So we investigated the ability of using these this very large simulated quantum annealer, which could simulate something like 32,000 fully connected qubits for tackling more challenging real-world problems. It has the ability to have a much higher graph connectivity and actually even start to experiment with higher order connections. So these are like hyper edges, which connect more than 2 nodes at a time. So can give you a slightly more compact energy representation of these models. So the energy function here is sort of a generalization of the restricted Boltzmann machine energy that I showed you before. And so basically we wanted to conduct some research using our simulated quantum annealer, which can run on very large graph sizes, how well we could generate synthetic samples for various types of data sets, including financial data sets and image data sets. An experiment that we did was basically testing how good our simulated quantum annealer compared to real hardware for generating synthetic data samples. So these are some results we show here. Basically what we show in this plot is a comparison between training an RBM, again, this restricted Boltzmann machine classically, which is in the green line here, using a real quantum annealer, which is provided by D-Wave in the orange line, and using our simulated quantum annealer as well, which is this blue PIMC line. And what we wanted to do was, as a function of training iterations, plot an adversarial error. So what we were doing was we were training our RBM models to produce samples, and then separately, for those familiar with adversarial training, we took these real and synthetic data samples and we sent them to a discriminator whose sole job was to try to predict whether or not the samples were real or fake. So you could say that the closer and closer to 0.5 that your model could get, which is like a 50% error of your discriminator, the better quality your synthetic samples are. So in this research, we were able to show that, again, both using hardware and our simulated quantum annealer, we were able to produce high quality synthetic samples that were able to essentially, within some statistical noise, more or less trick a discriminator model. And that it seemed to train much faster than the sort of classical RBM training. So there's a utility in using these models for generating synthetic samples, and it seems like using the quantum or simulated quantum approaches led to faster convergence of the models. We also used our simulated quantum annealer to do the same type of problem, but for that MNIST data set that we referenced before, except now, since we were able to have a much larger graph, we didn't have to do that coarse graining work that we showed earlier, and we're able to generate samples that looked quite similar to you know, handwritten data from the data set itself. So all of these samples are simply example images that were synthetically generated from our simulated quantum annealed trained models. So, and you know, obviously not all of them are perfect, but you know, this was a pretty exciting result for us. That again, these quantum trained models seem to be able to learn, you know, powerful sort of joint probability distributions, which is great. Switching gears a bit, we can talk about a different powerful model for generating synthetic data samples, which is called the quantum Born machine.
Quick question.
Yes.
Does anyone have reasonable intuition for why sampling from the RBM is more effective relative to others? Does it have a long forecast? Can it accurately predict well ahead?
So when you say, I might be misunderstanding your question slightly. So are you talking about the RBM model in general, or are you talking about the quantum component specifically?
I'm going to take a stab at in general.
Okay. And this is for like making prediction. So yeah, like, so the like Boltzmann type models are good at learning like probability distributions. And so for like the use cases that we're showing here, if you can learn like a data, you know, if you have a data set, if you want to try to generate new synthetic samples, these models have some nice properties where you should be able to train them to, generate good samples, because you're minimizing sort of the distributional difference between the samples generated from your model and the samples in your data. There are lots of different approaches to basically all of these use cases, which don't just rely on something like an RBM model. I suppose we could dive into that kind of stuff a lot, but yes, this is in reference to other sort of more like convolutional neural network types approaches or something like that. We're definitely going to tackle some other types of machine learning models in general, but I think this was a particular low-hanging fruit for quantum for a while because of the similarity of the energy function between Boltzmann machine models and these quantum annealers. It was just a very natural fit.
Okay, we're good here. Thanks.
Okay, great. So yeah, now we can move on a little bit to like what we call a quantum Born machine. So previously we were talking about these quantum annealing devices, which apologies if I didn't put enough intro slides into the actual quantum examples. I figured since there was a quantum computing group, there's probably some, I might be treading ground people already know. So quantum annealing is one type of quantum hardware which relies on, sort of this adiabatic theorem. So you start your quantum state in a well-known ground state, and then you evolve it over time into a more complex problem Hamiltonian. And ideally, you're staying in that ground state the whole time. It turns out, again, that you're more staying in something that's like a Boltzmann distribution. It's not exactly a Boltzmann distribution, but that was the type of computer that we were talking about for all of this, for all these previous Boltzmann machine examples. But now moving forward into a Born machine, this is a type of quantum machine learning model that can be run on universal quantum computers, such as those produced by my company Rigetti. And these are the more canonical things you guys have probably seen in a lot of quantum computing applications where you have quantum circuits which are built of single and 2 qubit gate operations. And a Born machine is trying to do a similar sort of training to a Boltzmann machine in a sense, wherein now our normalization is actually coming directly from the quantum state itself. So, like we were talking about before, you could write out all of the probabilities for every measurable basis state of your quantum system. And what you're doing with a Born machine is you're trying to essentially train your probabilities of all the different measurable states in a way that's driving it towards some distribution, wherein again, obviously the probability of measuring all of your states must be normalized to 1. So yes, essentially people have investigated these really interesting quantum circuit Born machines, wherein you start by having some quantum circuit with parameterized gates. So these are gates in your quantum circuit which you could tune to change basically the probability distribution of your quantum state after applying your circuit. And you again are trying to train in such a way that you change these variational parameters so that you're driving the samples produced from this quantum circuit to be measured in a way that the samples are similar to a data distribution. Sometimes using something like the KL divergence to help guide your training, which is a common technique for calculating distances between distributions. There's some great research papers out there. Some of our collaborators at the University of Edinburgh have done some great research into how one can try to have better cost functions for training quantum Born machines. So a few examples here are shown where there's a couple different types of cost functions, which you could think of in a sense as ways in which you can evaluate distributional differences. And one in particular, which is called the Sinkhorn function, and the MMD, which is mostly shown here, was shown to be able to train these Born machines to generate samples which were quite statistically close to target distributions, such as binomial distributions, and that they were able to show that this worked both on simulated quantum computers as well as real quantum hardware produced by Rigetti. So this is pretty exciting, and these Born machine models definitely are quite powerful in general. And so this was a great paper showing some different ways of training these models using different types of cost functions, and that they were able to train both on simulated and real hardware. There's also been some work into looking at how you could use these types of models in like a GAN framework. Provided here is a good paper for how you could use this kind of quantum circuit Born machine as a generative model, where you could have a discriminator either classically or with a separate sort of quantum discriminator as well. And the idea here again would be, using like a quantum Born machine to generate samples and mixing them with a real data set, and then passing those to a classical discriminator and trying to, playing essentially this Nash equilibrium game where the quantum generator, which is shown here, you're trying to change the parameters of your gates within this G circuit such that it produces over time samples that are harder and harder for the discriminator to determine if it's real or synthetic, while at the same time the discriminator can also train to improve its ability to differentiate at each iteration as well. So they're trying to eventually drive towards this Nash equilibrium where the discriminator can't get any better, nor can the generator. And that's when you should theoretically be generating very good samples. So this was a cool use case for using a quantum Born machines for this kind of like generative adversarial network sort of approach. And so then there's a slight jump again into a different topic. Not sure if there was any other questions so far to jump into, or we can keep on going.
Go, Max, go.
Great. Yes. Thanks again for all the great questions so far. So another, we sort of talked about this problem before, you know, when we were talking about this HHL algorithm, you know, for solving systems of linear equations. While we talked a bit about that there being issues with practical application of HHL, there's been some very interesting recent work for trying to use this thing called the quantum linear solver for doing the same kind of calculation. So figuring out how to solve the system of linear equations using nearer term devices. And this particular paper here basically demonstrated their technique could solve problems of size like 32 by 32 matrices, and using Rigetti, again, chips, and got good performance results as well as some degree of noise resilience, which is, again, one of the typical problems that's encountered on these near-term devices. Okay, so then, so touching on that, the next big chunk of this talk, and this will, you know, probably have a lot of interest, I think, too, and touch on some of these, touch on some of the questions that people have already brought up. But so in this section of the talk, we're going to move on to machine learning with quantum circuits and classical training. So the idea here is that we have these, you know, quantum circuits wherein we know that there's certain algorithms that that these circuits can execute that are not classically tractable. So the common use case that most people know about is like a Shor's type algorithm. So that is an algorithm for factoring very large prime numbers, and it's a well-known algorithm that is executed by a quantum circuit, and there's not up till now any known classical algorithm that is believed to do this efficiently. And the idea here is, well, maybe we could start to leverage the types of transformations that quantum circuits can do on input data to generate features of sorts. So sort of treating these quantum circuit transformations as feature extractors. And while it's, you know, it is by no means easy to have like theoretical proofs for the necessity that on a particular data set, a particular type of transformation is going to be beneficial, the sort of argument, I suppose, where there could be some advantage here is that if you could, you know, if you can find the types of circuit, the quantum circuit structure that produces transformations that provide a modeling benefit over like a classical approach, and it's sufficiently difficult to simulate, well, that sort of gives you then a quantum advantage. It's an interesting feature extraction that provides benefit comparatively to the same sort of number of parameters classically, and it's not easily simulatable. So that would be the sort of advantage that we're driving at with these sort of families of algorithms. And the general approach goes as follows. Basically, one is starting with input data, and that input data is encoded into the quantum system in a variety of ways. So this could be encoded into like the gate rotations, for instance, of a particular parameterized quantum circuit. The second step is actually running the circuit, and so processing this initialized encoded classical data by some kind of quantum circuit, and this again sort of provides the feature extraction, the feature transformation, and then finally extracting information out of that calculation, which requires like a decoding step essentially. So once you've encoded your classical data into the quantum circuit and you've executed the quantum circuit, you have this final quantum state, and then you have to define some way of extracting information out of that quantum state, which then is processed classically. So all of these algorithms sort of follow this three-step protocol. So encode classical data, process it using quantum circuits, and then extract data out of the system. An example of this is an algorithm called computational sinks, which was written by some other folks at Rigetti back in 2018, which essentially provides like a quantum version of an algorithm called random kitchen sinks in classical literature. They essentially, like you can see here in these little pictures, next to the letter A, they're starting out with this simple quantum circuit that's operating on 2 qubits, which are both initialized into the 0 state. And then they have some classical data set. So something like maybe they're XY points, and they're trying to predict whether or not they're inside a circle in like a unit square or something like that. So you have these XY variables. These XY variables then would get encoded into these rotational angles of these RX gates in the circuit ansatz. And then the rest of the circuit is executed, and then there's a measurement made. And these measurements are like snapshots that then would be interpreted in some sense as like features, and by running a bunch of these different circuits a bunch of different times, you generate kind of this feature set that you can build a linear algorithm on top of to predict, if, again, for instance, in a simple case, if a XY point is inside or outside of like a circle on a unit square. This research showed the ability of these quantum kitchen sinks transformations to provide nonlinear features. So again, a linear model cannot learn things easily like a circle as like a decision boundary, but you could train these types of circuit ansatzes, if you select the right ones, to be able to make decision boundaries like that, which is useful. But this approach overall didn't beat other nonlinear methods. They actually didn't perform as well. So I think compared against the support vector machine, this sort of kitchen sink model didn't do quite as well on a simple like image recognition task. So showed some interest here in like the ability to do some feature extraction using quantum circuits, but didn't show like an outright advantage over some other nonlinear classical models. Another example sort of in the same vein is this idea of quantum reservoir computing, where for those familiar with this sort of reservoir computing in general, there's models like echo state machines, echo state networks, and that sort of make a complicated Bath calculation. So you could picture there being this black box where there's a whole bunch of different complex nonlinear calculations being executed, and you're sort of trying to learn just a way of mapping your data into that black box and then mapping data out of that black box. So you're not trying to tweak all the parameters inside of it. And this is like a reservoir sort of computing type algorithm. And the similar algorithm was adapted just using like a quantum system kind of for this bath, and then using measured output to then feed into a model which can be trained for predictions using like this linear map. And so this is another example of, again, using like a sort of a quantum transformation for generating features and then building something on top of that classically. Then we can talk a little bit about one of the more recent papers that we've done in this space. So this is essentially a quantum variant of a very common machine learning algorithm, the convolutional neural network, or the CNN. Ideas of the CNNs, again, are just sort of doing a stacked set of operations that's trying to essentially extract higher and higher level features from an input data set. So in like a simple way, you could think about there being this like deep neural network, and it gets pixel values in it as input. And a first set of layers in this network might try to learn simple features like lines at different angles and things like that. And then these line features can be combined together to form more complex types of edge combinations. And as you work your way up, these sort of these sort of combinations of simpler features into more complex features can be used to form quite powerful predictions on your input. So as CNNs are quite commonly used in the real world, we thought that this would be an exciting opportunity to try out a quantum version of this sort of an algorithm. which I named the convolutional neural network, which is my favorite clumsy portmanteau. But basically, the idea here is to take a convolutional neural network, but as a first layer in this convolutional neural network, have a quantum version of a convolutional layer. And the way this works is as follows. In a convolutional neural network, you essentially take like an input filter size, which you can kind of see here as this dark or as this blue box in our input data here on the left. And you would, for each convolutional filter, you would sweep across the input data, and you would transform that input data in some way into like a feature. Without diving into and talking about CNNs all day, the quantum version of this that we came up with was that, well, what if we took these input subsamples of data, and instead of processing through this classical convolutional filter, we actually used those as values which we can encode into a random quantum circuit, and then generate sort of a feature activation after processing that data that's been encoded and decoding it into a single scalar output value. So this was kind of fun because it takes the same, it integrates exactly the same as a normal convolutional layer would, where once you specify within your convolutional layer how many convolutional filters you wanted to use, and ran that over all of your input classical data, you would generate output tensor blocks that are just like you would with a normal convolutional layer. But the difference here is that we think that, again, if there's an advantage, if the quantum circuits which generate the features show some modeling advantage, then we already know that in general they would probably be hard to simulate classically. So this could be an interesting type of quantum feature transformation, which would again have some advantage over what's seen classically. And the further advantage of this approach is that we really were trying to find quantum algorithms which we could run on higher dimensional data sets. So a limit for a lot of these early quantum machine learning algorithms is that data sets can be quite large, and the size of the quantum computers we have to operate on right now are very small. So how do you use a quantum machine learning algorithm on realistic data sets? But the convolutional neural network architecture kind of gave us a natural way past that dimensionality problem, because you don't have to map like a full image onto your quantum circuits. You only have to map subsamples of your image, like again in this picture where you're sweeping over the full input with these smaller blue boxes which are defined by your filter sizes. So this allowed us like an opportunity to run on higher dimension data, so didn't have to do coarse graining and things like that. So we were able to do this initial work, which has now been published in the Quantum Machine Intelligence Journal, and show that the addition of a single convolutional layer before processing it through the rest of a convolutional neural network stack is shown here. It's a little bit hard to see in this green line, but it basically beat a pure vanilla blue convolutional neural network in terms of hitting a much higher test set accuracy in fewer training iterations. We did compare it against a similar nonlinear pre-training sort of transformation, or we tried to make sure we were doing as apples to apples comparison as we could. So while adding these quantum features did provide a benefit over the same network, but with that convolutional layer removed, if we also compared it to a network that did a similar nonlinear classical transformation layer, and then we saw a very similar result. So this paper is sort of a step forward from the quantum kitchen sinks work in that it was able to integrate into a more powerful model and more clearly show a difference in terms of the modeling of the features was really useful in this convolutional approach over just the pure CNN, but that against other sort of nonlinear functions, it still wasn't like a decisive victor. So we're still trying to pursue this line of research to try to find again, maybe the right types of quantum circuits or the right types of input. And we'll talk about that a little bit later in the talk as well. But this was an interesting next step forward. And again, the papers are all linked in these in this slide. So for those interested after the talk, you can jump into all of these. We also had another more recent paper using, I guess, like a QNN 2.0, where we essentially tried to build off of our first convolutional work and improve it a bit by being able to process larger quantum circuits, which we were able to do by actually running on real Rigetti hardware. So the previous work was all done using simulated 9-qubit quantum circuits. And this work, which was for a satellite image classification use case, we were able to process larger quantum tensors by using our 28-qubit device that Rigetti has available for these experiments. And we were also able to preserve more of the classical data fidelity into our circuits. We chose an encoding protocol in the previous work, which applied a threshold that lost some of the classical information, which we think led to, again, less than optimal results. So we basically had this satellite image use case where now we have color channels introduced. So we're actually, I suppose, running on inputs that are 3D in some sense, where there's, they're 28 by 28 pixels wide and tall, but there's also 4 color channels in this data. And we were processing that sort of, that data through our improved QNN approach. And we tried our new approach running, our new convolutional network on that, as well as our old modeling approach. And basically what we saw is that our new approach, which is in orange, using our convolutional neural network, rivaled the performance of a different CNN, which was again not showing an advantage yet, but showing that again it was like again rivaling the performance of the classical network. And we think that the fact that the data set was much more complicated than MNIST is probably again where it didn't show a clear advantage this time. So we'd have to continue working to try to show that advantage on these more complex data sets, which is exciting. But it showed a clear improvement over our previous protocol running on the same data set. So we found this encouraging, and again, see this as like an iterative algorithm. We can continue to take what we've learned and keep trying to come up with a new version of the convolutional approach, which deals with the current sort of problems. And that's exactly what we're doing right now. And we're hoping to have like a phase 3 version of this paper later published, but that again is trying to rectify some of the weaknesses in this second approach as well. So
Max?
I'll pause here. Oh yeah.
Yeah, the question, it seems like your data encoding spans fairly continuous values. Does the continuous variable encoding show enhanced sensitivity to noise?
Okay, interesting. So we have done very little investigation in exactly how different noise in the input sort of impacts the performance using this like convolutional method. But that is an interesting point. So no, we haven't dived into that yet, but I think that would be that could be something that is impacting, and that would be interesting to look at in the future. But right now we were more or less taking the values of the pixels as being true and trying to just map them to variational parameters in the circuit.
Okay, thanks.
Mm-hmm. Yeah, hopefully that addresses that question. Thanks again for the questions. So yeah, for these machine learning algorithms using quantum circuits and some amount of classical training built on top, most of these have been within image classifications use cases, but we know, for instance, that CNNs are used for quite a lot of other applications outside of just image classification. So we think that this is an exciting overall approach to continue developing. And we list 2 of the kind of bullets at the bottom for things that we think quantum advantage hinges on. As we mentioned before, we haven't yet seen definitive proof of any of these algorithms in practice over other powerful classical variants yet. But we think looking for data with particular structure, as well as trying to find quantum circuits that are really good fits for that structure are quite important components for seeing that advantage. And we'll have a few wrap-up slides here in a little bit, which just touch on some of these points in a bit more detail. So I'll wait to dive into that a bit more. So I think this is one of the final overall topic sections before wrapping up with some what we think could be improved in the future. And are, again, open research sort of questions. So this last class of algorithms are these which are trained variationally with quantum circuits. So basically, like the last bullets here sort of says it all. Like before, we were using kind of these convolutional transformations more as, again, like a feature extraction of sorts. So once we defined our quantum circuits, we were running our input data through them, but we weren't yet then tuning any of those parameters within the quantum circuits. We were not trying to like variationally train those in those previous methods. And that's the key difference here with this sort of next group of algorithms, is that rather than sort of like fix the feature extractor circuits that were being run using these quantum circuits, they had some degree of training within those parameters. A great paper published in 2018 on this algorithm called quantum circuit learning sort of nicely phrases, gives some nice examples of this more or less. So their model is shown at the bottom as the classical counterpart to a neural network, where they show in these two boxes down here that you have this u of x and u of theta. So basically, they have this quantum circuit for transforming or loading your input data, which is in the X, and then this variational circuit that processes it for making some kind of classification. But instead of just generating sort of features from this U of theta transformation, they're trying to tune this part of the circuit to drive it towards minimizing this like loss function. So, train this circuit in the same way that you train a neural network directly to minimize like a cost function based on the input data that's encoded into it. So this is a nice review paper comparing it to, again, like the quantum reservoir computing example that I used before as a sort of quantum variant of these echo state networks, which again, don't tune the things inside the black box, just more or less how you map in and out of it. Another example of a variational trained quantum circuit was this work in 2018 for predicting, which is called which is this quantum variational classification algorithm. And this was shown to have some good advantage, again, for classifying data that was generated from a quantum circuit, which is shown in a rather confusing way, I suppose, here on the right. But more or less, they were able to show that they were able to train a similarly structured quantum circuits to learn parameters so that it was able to form a very good decision boundary between different generated quantum samples of a similar circuit. And these types of trainable circuits have also been shown to learn different types of nonlinear functions and approximate them. This work was able to show that, basically given classical input and wanting to decode it in such a way that you could learn different types of nonlinear functions. You see here on the right, there's different nonlinear functions here where you have this, initial and final, where you have like data points that are given by a teacher, which are used to minimize some loss function. And so, your teacher points, these blue points, are what you'd like your model to be able to generate after training. So you're trying to minimize the difference between where you're starting, which is this initial green line, and the final trained output of these quantum circuits, which is the orange line. And obviously there's some a little bit of imperfections, especially around some of the edges here. But overall, what this research was able to show, again, is that these quantum circuits could be learned to sort of fit these arbitrary sort of nonlinear functions, which is promising, again, just showing what you can do with these types of circuits. And one final interesting algorithm, I believe, in this section was actually this classification algorithm put out in 2019, which was able to show using a kind of clever data re-uploading trick that even with a single qubit, you could sort of map an entire neural network, which sounds a bit crazy, but they were able to show that using their using this data re-uploading protocol, they sort of were able to apply a very a series of gate operations to the single qubit that function similarly to like a hidden layer of neurons in a neural network. And by tuning all of the parameters of these single gate rotations, they were able to learn a series of rotation angles that were able to minimize a loss function on various input data sets predictions. So you see here, for example, there's a training set for trying to identify the different circles as different colors here, and using one particular quantum circuit and increasing the number of layers in that quantum circuit, which is similar to sort of adding more hidden units in a hidden layer. They were able to train and get better and better results, like you see over here, using just a single layer. These points are the points that are colored in are different predictions, and they don't fall squarely within the circles very cleanly. But by adding more and more layers in this quantum circuit, so more and more single qubit rotations, and then training all those single qubit rotational parameters, they're able to form better decision boundaries. And by the time they get to 10 layers, they're seeing some pretty good results here. Again, not perfect, but pretty good. And the downside of this approach is you do sacrifice gate depth, obviously. Like that's basically how they're doing the re-uploading trick. And in quantum computing, having really deep circuits means you're going to accrue a lot of error in real life. So this is a really interesting model, but you know, evaluating more of its performance on real hardware would be something interesting as well that I'm sure people are looking into. So I guess then the last couple slides here just sort of encapsulate some of the challenges of quantum machine learning that we're working on currently, sort of open questions and unknowns that some people are doing some great research on. So one question again that's really hard is that when we're doing these kinds of quantum machine learning algorithms to either extract features or train variationally to minimize some cost function, it's hard to know a priori what are the types of quantum circuits you should be using for the particular task and data set. So that's sort of an open question, and there's at least some interesting research for trying to form some measurements where we might get a better idea of whether or not a circuit is a good choice for the modeling task without actually having to completely train it and see how the results look. An interesting paper by Hannah Sim, shown here, evaluates some different, basically it formulates a few different interesting kinds of measurements one can do for a quantum circuit to essentially give a quantifiable parameter that might be useful in the future for, again, differentiating whether or not the quantum circuit in question you're looking at is a good fit for your data. They developed one idea in particular, which is this idea of like quantum expressibility that sort of says like how expressive is your quantum circuit. So basically how close to the Haar random matrix distribution kind of a thing you can get with your quantum circuit. So like how close to a random quantum circuit distribution is another way of, I suppose, saying that. But anyway, this is one interesting quantitative metric which could be useful if there's a correlation between the quantum expressibility of your circuit and certain types of modeling tasks. And there has been some recent research also showing that this might be, again, not a strong enough measure to show true correlation yet, but it seems potentially promising, and there's still quite a lot of research for trying to develop these types of metrics, which again you could run before fully training your algorithms and maybe pick better circuits. Another question is in relation to how we train circuits. I mentioned again this great paper by our friends at University of Edinburgh, where they were basically looking at different types of cost functions, which have trade-offs for training born machines, and have found that depending on the training method you use, you definitely can see big differences during the training in terms of convergence, and that each of these training methods also have a certain amount of runtime costs. So this is some kind of research that's ongoing currently, trying to identify which methods can train your models the fastest and also drive you closest to sort of like the true data distributions. But knowing exactly which of these works best, given your data is sort of still an open problem that is being investigated, which is exciting. Finding data that just seems more quantum amenable. This is another a bit of like a fuzzy, I suppose, research direction, because it's a bit challenging to fully define. We already got asked some questions again about like what is quantum data. So quantum data, again, basically the types of data which you like a density matrix of a quantum system, or related to data generated from a quantum circuit or something like that. But a lot of real life problems aren't necessarily taking that form of quantum data. A lot of real life problems might take the form of, for instance, language, which is entirely classical in some sense. It's quite unlike data generated from a quantum circuit. And what we've seen is that it's harder to show clear advantages over purely classical data using these QML methods, although there are certain quantum data sets that it seems like QML clearly provides an advantage because it's a structural fit. So trying to find data sets that maybe have structural properties that are just good mappings to these quantum circuits is an interesting research direction. Things that involve things that have like wave-like properties, for instance, and probably again are drawing on something physical at the end of the day. It might be good prospective use cases, but again, this is sort of like an open, interesting question. And finally, trying to figure out the best ways of encoding and decoding data out of your models is also a bit of a challenge. There was another nice recent paper about looking at what are better encoding protocols for mapping your classical data onto a quantum circuit, so that one, you're forming a really good decision boundary, which is kind of shown here in this cartoon, where you'd want to be able to identify the blue points on one side and the green points on another. But real quantum circuits have errors, as we've mentioned before, which you could sort of you could approximate an error for this simple system as like moving the decision boundary some amount. So can you encode your classical data such that you're both classifying it correctly, so sort of differentiating the different types of data well, forming a good decision boundary, and not only that, but like sort of maximally separating it so that you have these points which are very stable, so that even if an error is introduced into your system, you'd still get very high fidelity in terms of your accuracy with this decision boundary. So yeah, there's some interesting recent work looking into that are these robust encodings, but this is something to continue to look at, and we in particular right now at Rigetti are also looking at some novel approaches for new sort of decoding protocols methods, which have some promising properties as well. So I think then this finally wraps up the talk. So for those of you still here, thank you for bearing with me, and apologies for any ramblings, but happy to take any more questions, and hope this was useful, and that the paper references will also be useful for those that get a chance to go over that later.
Thank you, Max. I've got a couple questions already typed in, but before we get to that, the good news is I ordered a pizza for you so that we can go another hour and a half of your time and compensate you. Unfortunately,
great, thank you.
I don't know exactly where you live, so I sent it to the house at the corner at the intersection of Broad and Market in Philadelphia. So somebody walking in City Hall right now, I get a free pizza. thanks
That's
to
a good
your
deal for
labor.
them.
Yeah. And I'm sure there's a lot of people walking around City Hall right now, you know. Anyway, you're getting quite a bit of buzz from the folks down in Australia. So I'm going to recommend to your management, and you may want to take it up, that maybe you get a trip down to Australia to answer some of these questions in person. But one of them is unitaries are linear, and many of the interesting behaviors of neural networks come from nonlinear activation functions.
Mm-hmm.
In general, how do we get the nonlinearities in quantum circuits? Refining it based off that slide where you do the nonlinearities
Mm-hmm.
come from with a stack of linear transformations.
Yeah, so that's a great question, and yeah, we have some excellent folks that I've had the privilege to work on from Australia. So some of those folks might be out there. Yeah, so this is actually a really interesting question that is completely true. So this has been a particular challenge actually using photonic quantum computers. Some quantum computers are essentially just extremely linear, and we know that any sufficiently powerful machine learning model needs to be able to capture nonlinearity. So yes, how do you do that? At least in what we've done, essentially the nonlinearity comes a bit from the decoding process. So the way that we are decoding the information is not linearly reversible. So making measurements and processing the data collapses the wave function into a single measurement, and then we make our final sort of feature built off of that. So there are also other interesting ways of injecting nonlinearity kind of into these circuit transformations. Like I believe one way is sort of making partial measurements. So applying a quantum transformation and then measuring a single qubit, which adjusts your whole wave function in an interesting way, and then continuing to evolve the system with future transformations. So I think both of those are like ways that we have the nonlinearities introduced.
Whoops, I was on mute. Got one more here. Bear with me.
Yeah, no worries.
I got user issues. On slide 45, could you discuss the metric for circuit expressibility a little more?
Yes. So right. So there is essentially like the expressibility metric. I suppose I can use this picture a little bit. I didn't talk to it that much. But so in this picture, we have like 4 different circuits, and you see right below them is the very typical block sphere. So this is like a visual representation of like the quantum state of a single qubit. And if we start in the 0 state and then all we do is apply the identity operator, we haven't changed anything. So the probability of measuring this particular quantum state from this circuit is 1, that we should measure this to be in the 0 state. So you see that here in the distribution immediately below that, where the distribution of the idle circuit is 100%. So we show the fidelity to 0 basically in this circuit. So basically what we see in that bottom distribution is if you measured this quantum circuit after applying, if you measure this quantum system, the single qubit, after applying the circuits in this top row, what's the fidelity to the 0 state? So basically like, if you don't move from the 0 state, you have 100% fidelity. But as you start to apply these different gate operations, you have the probability of, you get a different fidelity there. So that's essentially what you're seeing is like those blue points on the block sphere become like potential measurements is basically what you're seeing. And so eventually as you add a deeper and deeper circuit, you sort of move towards this random distribution, which is the Haar distribution that ends up being a uniform distribution for a single qubit. that if you could essentially say this is the most expressible circuit if it's able to do what like an arbitrary unitary distribution would give you. So I suppose expressibility in that sense is it's a distributional difference defined by the KL divergence between the hard random distribution and your circuit's distribution in terms of this fidelity. So that's rather long-winded, but that's more or less the metric here for expressibility.
Question for you, Max.
Yes, shoot.
Yeah, thanks for the for this deep dive. I find not all QML presentations go this deep, and don't hold back at all. So I didn't understand everything, but I can appreciate the research you do, and that's the nature of my question. So it seems like the research you're doing is fundamental to QML. But you're employed by Rigetti, and so as I try to understand more about the industry, I'm curious how that works out for Rigetti, because I primarily see Rigetti as a hardware company, maybe secondarily as a software stack, but then I'm curious how large, of a research division that is there at Rigetti, and then also does your fundamental research have to be tied to, revenue generating opportunities or working with partners? So pretty extensive question. You can tackle it however you want.
Yeah, no worries. Yeah, so I think at least for Rigetti, the Rigetti's aim is to be like a full stack company. You're definitely right that like the fundamental business still lives on the hardware evolution. But from what we believe, at least in the industry, you need to show practical use cases of that hardware to get real interest. And we kind of see there being this virtuous cycle, which I suppose you could call like deep integration, where we think that the first algorithms which show quantum advantage will require quite a lot of like iterative performance cycles, where there are going to be things that people in the sort of software interface level with the quantum machines are learning every time every time we come up with a new experiment. And similarly, we're going to learn things like at the applications level about what is possible on the hardware every time we try a new algorithm. So you're absolutely right. My main focus has been particularly trying to drive at these quantum machine learning use cases, which ultimately, if you're running it against hardware, are going to show where there are opportunities to sort of make the algorithm more performant by making it better suited for the hardware itself. And then there are ways of doing that that's sort of, I suppose, iteratively, for instance, how we improved our QNN 2.0 is making it a better fit for like Rigetti hardware. And subsequently, you get a good classification or a good benchmarking, I suppose, for knowing where are the fundamental bottlenecks and issues with like hardware error rates that prevent certain algorithms from being useful at a certain gate depth, for instance. So it's I think like an interplay, I suppose, where you do ultimately, to get I think certain like partners interested, want to show real world applications, and to make those as performant as possible requires a pretty deep integration level with the hardware itself. So that's I think kind of how we're seeing things right now anyway. But definitely yes, the sort of without even knowing certain applications, the hardware folks continue to work on improving just the fundamental hardware performance based off of more error benchmarking things that they can do regardless of use cases. Like they can try to push on increasing T1 and T2 times and things like that, but without really needing to worry about what's the high level application. But something like, for instance, a circuit topology, like the way that you build the circuit, like the possible 2-qubit gate operations that are between qubits in the circuit, that could be something that's like application driven, but for example, so you might want to have that kind of feedback for like what's the best hardware graph for a particularly interesting QML algorithm, and then anyway, so a bit of a long-winded answer, but yes, that kind of research is still quite important, I think, probably for all hardware companies, and whether they're doing it internally or with partners, I think that everyone's trying to figure out how hardware devices perform on use cases, whether they be machine learning, optimization, or chemistry, or what have you.
Hey, if you allow me to add my 2 cents, I mean, it was a good question in that what I find, and I'm new to this industry, is that, it's really profound that, believe it or not, we're all working together, even what normally would be competitors, and as we're all trying to build a pie, and we all have an interesting objective of all trying to make a quantum computer useful, and get one actually useful to the business units out there. And we're all trying to get smarter. So, if I were running a hardware company, I'd have guys like Max out there, because my hardware may not work, and I'll still be positioned to be able to benefit, from the industry, et cetera, because, so we're all kind of working towards the same end, and we're not really competing yet, except for Google and IBM, obviously. But that's what makes this industry quite cool. Anyway,
yeah.
I think Mike, yeah, go ahead. Yeah, Max, go ahead.
Oh, no, I was going to say, I agree. And I do think it's a particularly interesting just field to be in, where I do think that there's quite a lot of really good blood and collaboration. And I think a realization that the field itself will be much better off if everyone is doing well in general. So yes, I think that's totally true.
Mike, did you have a question? I might be having unmute problems. Anybody else in Zoom?
I think
Mike, are you talking?
Go ahead, Mike. Helen, you're next.
Somebody
no question.
Oh, go ahead.
No questions. I'm sorry.
Oh, okay. All right. Helen, you want to read that one off?
So Pat asked, does Rigetti working on quantum storage where we can store quantum data the way you have discussed, or we still need to use classical semiconductor storage?
Oh, that's interesting. Thanks, Helen, for relaying that. Yeah, so we've definitely been focusing more on the compute elements, I believe, not as much the storage yet. So there are some people looking into that, I believe, but I think Rigetti is definitely focused on the compute rather than the storage at this current time, as far as I'm aware.
Okay.
But Max, wouldn't you say, I mean, if we don't get to the world of QRAM,
Mm-hmm.
would the machine learning algorithms really be helpful, really help? I mean,
yeah, well, that's kind of the benefit of like and apologies, I feel like I might need to shorten the slide deck at some point, because I always feel like I'm bouncing between over explaining but then realizing there's quite a lot of other content to get through. So apologies if I've skipped over some things, but so at the beginning of the talk we mentioned like HHL and Grovers, which both do require QRAM, which are both a prerequisite for a lot of quantum machine learning algorithms like quantum k-means and quantum PCA and things like that. And the sort of main stuff that we talked about though in the rest of the work that we're looking at, such as the parameterized quantum circuits for feature extractions, or for Born machines, for generating synthetic samples, those don't really require QRAM, is kind of the beauty of it. You're not having to encode an entire data set into some kind of random access memory that the quantum system has access to. You're sort of processing it live, sample by sample. So there is a trade-off then where you have to sometimes call many circuits many times because you're sort of processing it on the fly, but you don't have this fundamental issue, which I think some people still worry that QRAM's never really going to fully evolve, and that would be a bit of a death note for certain types of algorithms. But I don't think that yeah, all things being said, I don't think that it's for all these algorithms, it's not a prerequisite that you have this like kind of QRAM thing. You're more concerned with like gate depth of the circuit itself, which that impacts directly your total accrued error of the circuit. So hopefully that helps.
Good news is, folks, this is recorded, so you can listen to it again as you become more knowledgeable. I'll listen about a year from now when I climb up the curve here. All right. Well, I know we have somebody from Luxembourg on the line somewhere, and it's almost 3 a.m. Last call for any questions, out of respect for the Luxembourg folks.
Yeah, I appreciate the global. This has been one of the interesting parts of these Zoom meetings is just the ability to have these really cool global chats with a whole bunch of people at the same time. So appreciate everybody that has come out and stayed late.
It's a lot of fun. Actually, folks, Max was actually going to be a speaker for us physically in Philadelphia and Harrisburg before all this, and I was tempted to delay his talk until we were able to go in person, but I decided, there's so much interest in machine learning and quantum machine learning that, we just had to get you out there. But I do expect, Max, we'll be inviting you once we get out of this lockdown mode, and then I'll be able to get the actual pizza to you for real.
Anyway. Yeah, that'd be great. I love that.
Yeah, okay.
It'd be really fun.
Last call. Anybody?
Yeah, I'll ask another question.
There you go, Amir. Yep.
Max, curious, you gave a small bio, but it'd be great to hear a little bit like a condensed version of your journey into quantum computing, maybe like even some interest points from you that steered your, I know you talked a little bit about your background in physics, but I'm curious if you could expand on that a little more, like your journey.
Yeah, no, definitely. Yeah, and this is always, hopefully for the 2 cents that it is interesting, because I know a lot of people want to get into this community and it's a bit of a rocky or confusing road sometimes. But I got a little bit lucky. So I was like one of the Lockheed Martin's longest interns. I worked there all throughout undergraduate doing various engineering projects every summer while doing my physics undergrad. And I didn't particularly love the engineering projects I was doing. So when I joined grad school, Drexel University here in Philadelphia, go Drexel. So when I started my physics PhD at Drexel, I was going to stop working at Lockheed, and that just so happened to be the year that they bought the first commercially available quantum computer from D-Wave back in 2011. And my previous bosses knew me and knew that that's, it's hard to turn away quantum computing from a physicist. It's extremely exciting. So I sort of jumped onto that and continued to work every summer part-time doing research at Lockheed on quantum computing applications, while at the same time I was doing biophysical neural network modeling for my PhD thesis at Drexel. So trying to model sort of the complicated biophysics of real neurons in like a network to try to, for instance, see the impact of aging in a brain from like a biophysical perspective. And that actually naturally led me to get quite interested in machine learning. And so the sort of blessing for me is that I got to, due to my physics and interest in engineering, get the chance to mess around with these early interesting quantum computing devices, and simultaneously my thesis work sort of naturally led me to get quite interested in how models can be trained to learn different tasks. And then you start to get into bottlenecks with machine learning, and that's a natural extension to start thinking about where you might be able to use novel compute architecture, not just quantum, but the whole world is looking at various kinds of tensor networks and neuromorphic computing, different ways of speeding up, complex algorithms. And I think that's for me like where something like a meeting in the middle between quantum and machine learning is a really exciting space to be in currently. And quite a lot of other folks that get into the field obviously are going through a more traditional PhD in a quantum subfield or doing research now in a quantum computing, major specifically. And there's quite a lot of internships and other things available within the quantum computing world for those interested as well. So I'd always keep my mind's eye out for that. But that's a little bit of how I ended up here.
If I can delve a little deeper, so if you can reflect a little bit on it, Max, what quality inside of you has, I mean, that's a pretty tough ask to be working like that for 9 years and such a tough topic. What kind of people, what is it inside you that got you through all that? Because that was no easy climb, or was it?
No, it's been, I mean, I think that's one of the things where like I think I'm very curious by nature, and I think like I very much like, I like to feel like there's a lot of freedom in what you can do, and so constantly pushing on the bounds of what you can currently do, I think has been a good motivating thing. So quantum, that's been to me the biggest joy, is that like quantum computing is hard, and trying to do quantum computing applications for subject matter you've never studied before, like trying to figure out how to apply complex mathematical algorithms to map hard problems in like oil and gas, or a complex optimization within a pharmaceutical application, to again this extremely difficult new computing architecture that nobody really fully understands yet. It's I think like that sense of challenge and newness. Like I think that like it'll be at the very least something I can kind of look back and say from like a legacy perspective. You got to contribute towards a pretty magical time in this kind of new field, and there's a lot of far brighter people than I doing bigger things in the field, but I think it's a pretty motivating thing to be able to be to have been on the ground floor on a couple of these interesting research projects that hopefully grow into a really promising technology. So definitely, I think that general curiosity and that feeling that, we really are working on something that could be really important to quite a lot of people in the future is very motivational to me anyway.
Yeah, it's interesting. You've been fairly lucky in that you've been able to grow with the field. And, new entrants like myself and many others, it just seems like an overwhelming challenge. But, I agree. If you just stick it out, 3 or 4 or 5 years from now, people will be asking you, meaning us, that same question. And 'cause it's just hard, to catch up.
Yes.
But really, would you agree that we're still in the infancy of this industry, and any of us on the call here, if we stick with it for 5 years, we'll be you in 5 years. Of course, you'll be 10 years ahead of us.
I completely agree. And this is, I think this is one of those interesting times where there are just now starting to be a bit more formal programs for people, again, that aren't enrolled directly in like a quantum computing PhD or something like that, or already working for a quantum computing company, to get more actively involved. There's a huge recognition that quantum computing as a research area just is not going to have enough people that know how it works as the need grows. So simultaneously, getting people plugged in, like I mentioned, has been hard. But one of the promising things I've gotten involved with that for those interested might want to search out, the acronym is QOSF, but it's basically a community of sorts where it's trying to pair up mentors that have some quantum computing experience with people that are trying to get into the field and doing like mini research projects. They don't have to be something that's aimed towards making a research publication, because that can be quite difficult and take a lot of time. But yeah, with it has quite a lot of resources for people that are interested in learning online. And then there's, again, some of these interesting parts of the program as well, where you might actually get paired with someone. Like I'm working with one person in particular, trying to help them investigate one potential line of research. And there's other folks that are like working with this program, and hopefully it's a success and continues to grow. But there are some things out there like that, and people are always posting some new tutorials and things online. So there's and this QOSF keeps good track of all of those sort of online tutorials and contributions as well. So I would heavily suggest searching that out, and hopefully, yeah, that continues to grow, because yes, I think people interested now, if they get involved 5 years from now, are going to be very well positioned as hopefully the hardware is improved and there's a lot more interest in getting more people as like a paying job doing this kind of work.
Well, thanks, Max, for that. Amir's kicked off a new track here in conversation. You okay with this? We got one more type of career question.
Yeah, sure. Go for it.
You sure? Okay.
Yeah.
It's getting so late, I can hardly read it anymore. Would you have any advice for mid-career professionals who have a physics background, have been up there with their quantum mechanics and machine learning coursework to get in this field? I think you kind of answered that, but
yeah, I think it's a great question. The starting places, I think there are some, again, great resources to learn particular things. I think coming in with already a subject matter strength is quite important, and that can kind of be a nice stepping stone. Like there in my mind is still quite a lot of low-hanging fruit. So trying to form connections with people within the quantum computing community, leveraging your already strong background in certain technical spaces, can yield to some really good potential research opportunities. So I think, like, you know, it's always great to try to look for opportunities where you can learn, again, things from demos out there, but also look into maybe trying to take something like a demo and see if there's like a problem within your subject matter space where there could be an interesting research paper opportunity. And, you know, putting even something on the archive can be a great starting spot for a lot of folks. So yeah, I think that's probably a good suggestion outside of, again, deciding to do a whole nother ramp as like a thesis thing. But
okay, well, maybe we can pull you aside someday and just tap your brain on career advice someday. But I think that's probably it for tonight. We've been running over 2 hours here. Max, thank you very much. It's been great. It's been a great talk, and the career advice is certainly helpful to all of us. And I don't know about the others, but I suspect they'll be like me. I'll be watching the replay once I learn a little bit more about it. So,
yeah, no.
Thanks. And we'll be watching for your papers too, by the way.
Yeah, thank you very much. It was great to chat with you all tonight, and thanks for sticking around. 2 hours is a long time, so appreciate the time.
All right, ladies, gentlemen, thanks for coming by. Max, again, thank you. And that's it from here. This meetup, we've got another event coming up in 2 weeks. Just watch the website for that. I'd recommend watching the Washington, D.C. and St. Louis and Columbus, Ohio, and I can go on and on. There's lots of good material coming out right now because of the lockdown. So I hope to see you all out there, and that's it from here. Thanks, Max.
Cheers. Have a great night.
Bye-bye.